Okay, color weather radar. Let's have a look at that. Another pulse system. So weather radar systems in general are designed to detect the presence of rain, storms, violent air turbulence, etc. And the information is then displayed on either an old school cathode ray tube or a more modern liquid crystal display screen. The airborne weather radar system typically operates SHF, so super high frequency. It could be on either C-band. C-band is up in the super high frequency range from 4,000 to 8,000 meg, or 4 to 8 gig, if you want to put it that way, or X-band, which is 8,000 to 12,000 meg, or 8 to 12 gig. Again, the weather radar system operates like radar altimeter, and for that matter, transponder and DME kind of. It's kind of like the echo reaction principle, where you send out huge amounts of power and you expect a reply, a bounce back.
Hey Darren, are you sharing anything right now or no?
Oh, am I not sharing it? Yeah, I should be sharing it.
I can see it just fine.
I can see it fine, Darren.
Yeah, it's not fine too.
Okay, it's just me then.
It's just you? Okay. Just you.
Figure it out.
Figure it out. Yeah. So, as you can see from that aircraft, I think where we know where the weather radar antenna is going to be housed. Looks like it's going to be forward looking. So it's going to be in the nose section, probably under a radome of some type. So the pulses then, and this thing can go out 200 to 250 nautical miles, are going to strike a target, which could actually be weather, or it could be a mountain, or even another aircraft. And a portion of the energy is going to be reflected back to your radar antenna. Like I said, the range of this system is out to about 250 nautical miles. And again, because it's on the frequency it is, in the super high frequency band, C-band and X-band, you want to get the aircraft nice and high in the air. And yes, they have them on helicopters as well. Typical weather radar system consists of an RT unit, so you always need an RT unit. Some kind of display, we're thinking a display screen would be good. A control mode, so that's a mode selector to select what mode of operation you want the radar to be in, and some type of antenna. The more modern types are called the flat plate style antennas. Okay, so RT unit, display unit. This one's got a built-in mode controller at the bottom, and that one's got a flat plate style antenna. So as previously mentioned, the radar antenna is going to be mounted in the nose section of an aircraft, protected by composite, so non-metallic streamlined covering, referred to as a radome. Remember, when it comes to radomes, we don't want to paint those with any type of metallic paint, because the RF energy needs to be able to freely, in straight lines, penetrate the radome and come back in through it. That's what that says, okay? And I don't know if you remember when we were taking the different types of noise and how to sort of suppress, corona and all of those other things. The radome is kind of a special animal in that you got to still figure out how to bond it properly, so it doesn't build up static. So the more modern type of antenna is indeed these flat plate style antennas, as opposed to sort of a parabolic or a concave dish type antenna. So the signal, so this antenna, the first thing we got to understand about this antenna is it's gyroscopically controlled. What do you mean? So they refer to this type of radar as forward looking. It's forward looking. So if you want to look forward and you pitch nose up, then the antenna, in order to continue forward looking, has to pitch nose down at the same time. So it's got to go down as you go up, and as you go down with your nose, it's got to go back up. If you kind of bank to the left, it's kind of got to go right, and if you go right, it's kind of got to go left in order to continue to look forward. Okay, so it's gyroscopically controlled, so it's able to do that. And as far as the system as a whole goes, we're going to identify weather conditions by color. Hence, it's called color weather radar. And a couple of views here. This is sort of a standard view where you're looking at what's in front of you. This is in weather mode. You'll notice that when it comes to modes, there's also something called map mode. You can ground map with a weather radar system. You can tilt the radar antenna down to look at the ground using the panel tilt here. So this is sort of your standard mode, but you can also flip it over to a profile mode and look at the sort of the intensity of that storm in a profile mode. See how thick it is. Sometimes flying up or flying down could be a problem if this thing is everywhere. So when it comes to colored weather radar, black areas indicate clear conditions, smooth sailing. That's good news. Okay, green, however, indicates some light cloud conditions, followed by yellow areas, which is increasing thickness of weather condition. Red is now indicating a concentration of heavier weather formation. Now, on a 3-colored radar system, that's the extent of life. This is it here. You get, 3-colored radar, you get green, yellow, and red, kind of like a stoplight, okay? But if it's a more modern radar system, they add in a 4th color. What's scarier than red? Is there anything scarier than red? Trust me, I got them in my living room. They're my curtains.
Pink.
Yeah, magenta. Magenta, that indicates a concentrated weather condition such as hail or thunderstorm. So it's getting bad when the color goes magenta. You can tell this was an afterthought in the design. They should have put magenta before red, but okay. I don't know about you, but magenta doesn't seem as scary as red, but it is scarier. So when it comes to these colors, what it really all means is green is light rainfall up to 4 millimeters per hour, whereas yellow is light to medium rainfall from about 4 to 12 millimeters per hour. Red is heavy rainfall, 12 to 50 millimeters per hour, and magenta, go back here. Magenta is very heavy rainfall, over 50 millimeters per hour. So over 2 inches per hour on a 4-colored color weather radar. That one. So the 3-color weather radar, and the dead giveaway for me here is 1, 2, 3. You only got green, yellow, and red. So this is a little bit of an older weather radar. You can see the sort of the legend down here as well. And this particular weather radar, just looking at the way it's scanning, has been put in sector scan mode. So it's only scanning 45 degrees to the left of your nose and 45 degrees to the. It's called a sector scan. Okay, and the scarier colors, of course, being the red colors here. Black is great, clear skies. And like I said, even though this is a gyroscopically stabilized antenna system, you do have the ability with your gyroscopically stabilized antenna system to tilt your antenna to look down a little bit. So we can see we can look down here, tilt down or tilt up. Okay, this one's looking like tilting up and down about 12 degrees if you want to. And a 4-color color weather radar adds in the magenta, so we can see colors 1, 2, 3, 4: green, yellow, red, and magenta. That would be a little bit more modern, adding in the magenta color. And so traditional mode is sort of looking forward all the time. Let's not forget that other important color when it comes to color weather radar. And don't tell me that's baby blue. What's that color? Cyan. Okay, so the colors when it comes to color weather radar are black, green, yellow, red, magenta, and cyan. And again, the profile view. You can look at the thickness of the storm. And you can see you can select different ranges, how far you get range markings, how far you want to look out. The system can look out pretty far, as far as 200 to 250 nautical miles on the screen. So pretty important when you're dealing with any kind of radar system, specifically this color weather radar system, because it's putting out so much power. Okay, we're talking about, kilowatts of power, 10, 15 kilowatts of power. It's important that we inhibit it from transmitting sort of when people are walking around it, when it's on the ground. So the radar system shouldn't be turned on the ground unless special precautions are taken, because we don't want people walking in front of it when it's working. Because the emission from the radar antenna can be pretty hazardous to a human being. You won't notice it today or tomorrow, but down the road, you'll wonder why you got these weird, tumors and growths and cancer. So never walk in front of an aircraft when you suspect that the radar antenna might be actually working or activated. It's pretty hard to tell. But like I said, this one's pretty wimpy. The output is only about 4 kilowatts, but some of them are up over 10, 15 kilowatts of power. So that's a lot of power. Now, don't mistake color weather radar for another system people refer to, StormScope. Okay, made by that ever so popular company 3M, the makers of sticky pads. Okay. So and bad license plates apparently, right? The ones that reflect things improperly. 3M StormScope is a system that can also look out about 200 nautical miles. You see the range settings here, and it paints little red X's or little red X's on the screen, not to indicate necessarily hail, or it's a lightning detection system. So it's lightning locator or lightning detection. And where there's smoke, there's fire. If there's lightning, there's a pretty good chance that there's storm activity. Okay. And there was another company that after 3M came out with their StormScope for aircraft, this company, it's actually a Canadian company, Insight Avionics, they came out with their Strike Finder. It's the same sort of thing. So anywhere on the screen where you see little red markings, right now we're in the 200 nautical mile range. That's lightning activity. Okay, so this thing will sweep clean. It's kind of like a sweep antenna. It sweeps and it'll clean off, and then if you see it replenish red dots, that means the activity continues. Okay, so don't mistake color weather radar for StormScope or Strike Finders. StormScope or Strike Finder is specifically lightning discharge. Ooh, what's that? Got some links? What's the links do? Let's have a look. Oh, this is, let's see. This is a GPS light.
There's a cluster of weather there, but you can see
interesting.
Though it's reaching out and striking our airplane, which of course is not the way lightning behaves, at least most of the time. So this is what the radial spread. There is a storm, but it's within 50 miles. We zoom in on this, you can see that the outside of 50 range. Since the tops are only 30, I'm very comfortable with that. There are rain showers out the window within range, within that 30 miles range. At least as far as we can tell. Easier to see that at night, but go to the radar, we can see that.
Okay, so that radar is kind of nice. So they got, in addition, and that's a pretty fancy GPS because it's got now GPS and Strike Finder. In addition to that, they've got their color weather radar here going, doing a sector of 40 nautical miles. And our problem seems to be over here on the left-hand side, our heavier storm activity. I don't know if he goes to profile view so we can see the thickness of this thing, but it's like both units.
We really have only very worse light gray.
And you can see how the nose-mounted gyroscopically controlled antenna is actually moving. So you can see in the sector scan, this is your beam. So it's rewriting every time it's doing that sweep. It's rewriting the page. Okay.
380 in the target position. Delta 21.3 forward side. Discussed earlier, that's going to be under us. We explore that 360 bearing pointer. Go right around the weather at the Cowboy area up there. Right to the center, about the 5 right. Then check that vertical profile and see what it says.
So there's the profile view. Looks like they can go up.
See that might be some range below us or above our altitude. Right approved and the Mark 1 eyeballs are supporting that. Hypothesis. Under 135.4. Look out there. We really don't see anything directly in our path. We're going to pass over even the lowliest of the highest directly in front of us. American 1241 finding team follow. So yes, there's weather here today, but we have a wide berth. We have at least 30 miles probably heading for your climb. Heading American 1241. My safely. Center Delta 2103, we're direct. Tango Charlie Charlie at this time. Delta 2103, right, thank you.
Yeah, so that one was pretty good. What does this show me? Yeah. What? Guess I'm not supposed to get rid of that. Yeah, that's good music. Hey, nothing else? Here, let's try that again. Unexpected error. Okay. Unexpected error. Got that. Put it in. Where can we put it? Yeah, put it there. Okay, let's have a look at this. Fancy music in this one. So that's just a self-test. So range 30 nautical miles out. Okay, 50 nautical miles out. Starting to look a little better past that. So we turn the stabilization off. Now he's going to tilt the antenna. Well, there you have it. Data showing us ground mode. It showed us most of the modes on there. On that one. Oops. Put that back up here. Good for the weather radar. Okay. Which brings us to close to the end. I gave you a handout and you said, wow, it's in color. A lot of yellow on there. Yeah, GPS, global positioning. So let's get a head start on that, unless you have any pending questions from radar or radar altimeter. Okay. So let's move on. So the GPS system, global positioning system, it's really called the Navstar GPS system. So the Navstar part is the navigation, satellite timing, and ranging global positioning system. Not to be mistaken for OnStar, the famous GM product. So Navstar is quickly. Yeah, it's already passed is quickly. It's a range navigation. And the current GPS system that we know and love started way back in 1973 with experimental satellite navigation programs, obviously stateside. The first program they called the U.S. Navy's Timation program, and the U.S. Air Force's 621 project came together to become the Navstar global positioning system. So why did the Americans want to do this? They developed it for military application to provide worldwide three-dimensional information consisting of latitude, longitude, altitude, speed, and there's method to their madness. Okay, this is why they wanted it. Was intended for precision aiming of weaponry and accurate troop deployment. So it was first successfully tested and proven in the Gulf War. I don't know if you guys were even alive for this when Kuwait got invaded by Iraq, and the Americans went in old George Bush, not George W. Bush, George Bush, and I guess liberated Kuwait. And the first time they were using this this GPS system, and it worked flawlessly. It worked well. And I believe that was called Operation Desert Storm. They drove the Iraqians out. They implemented Operation Desert Shield to protect Kuwait. So for civilian use, the GPS can tell on the Earth's surface or in the atmosphere, a little harder to do within the atmosphere, to approximately 30 meters. How fast you're going, 0.1 meters per second. It can also tell the time to within 1 second. It's using an clock. So apparently this clock won't change 1 second in 70,000 years. So I won't be alive to verify it, but I'm going to take their word on it. So military specifications are even more accurate, but not necessarily completely available for civilian use. The main advantages of this GPS system start with its accuracy, its worldwide application, kind of nice. The fact that the signals are not easily contaminated by bad weather conditions. And the disadvantage is only really one disadvantage of the GPS system, and it has to do with the owner. Okay, it relies entirely on the fidelity of the satellite data transmissions and the charge of those satellites. So we're enjoying this because the Americans are letting the world enjoy this. And I believe the handout I gave you, I included the more modern Garmin. This is the GNS 530, and that's the 430. The GPS has certainly come a long ways over the years. That's a lot more stuff. Looks a lot nicer too, incorporating comm and nav as well. And it appears it's not only incorporating comm and nav, but it's incorporating lightning detection, as per the last video we saw. So when it comes to GPS, I'm pretty sure satellites are in the orbit. So we kind of need a top on a fixed wing aircraft. That's not much of an antenna, okay? So we're talking about a little flat antenna, tiny little antenna. So the frequencies must be up there again. A good location for a GPS antenna. Helicopter, that's actually a pretty popular location if you can get the damn wiring routed there on the top of the sort of the vertical. You're gonna see it on the roof. So I do like this location on the tail, except that's a lot of wiring. First to call it the tail boom, through the fuselage, up through the floor panels, and then to get to the GPS unit in the cockpit. So even though that's a decent location because it can see the sky nice, is that, you know, the longer you have a piece of coax and the more connectors you introduce in the run, attenuation, the more loss. And we're kind of, this is almost like, you know, if you ever had somebody align your Bell television dish, they're looking for maximum signal strength, right? The more line you have, the more connectors you have a little bit of loss there. So maybe putting it, you know, above the pilot and co-pilot here on the roof is not necessarily so bad to the instrument panel. The only bad part is there may be an issue with blade passing frequency. But that in this particular aircraft, I don't think it would be a problem. There's enough distance, probably be fine. So theory of operation for GPS, orbiting satellites, and there's a lot of them, are going to transmit coded pulses. First and foremost, contain the satellite's position and the precise time at which the coded pulses were sent. GPS receivers are going to measure the elapsed time and then convert that into a distance. But from 3 satellites in orbit. Two-dimensioning is available. Three-dimensional positioning, you actually need a 4th satellite. You have to acquire a 4th satellite, and you need that timing and calibration for 3-dimensional positioning. Not a problem, because supposedly, according to our American friends, at any given time or position, you should be able to pick up a minimum of 5 satellites. You should be able to. There are some spots that seem to be hidden. Trilateration. GPS receiver needs to locate, if we want 3D mode to operate, 3-dimensional positioning, we need to locate at least 4 or more satellites. For this 3D accuracy, the merrier, the better the accuracy. Once the satellites, once the receiver, and all GPS receivers are indeed receivers, once they pick satellites, then they can use trilateration to locate your position either on the Earth's surface or in the Earth's atmosphere. Right smack dab in the middle. So once the GPS receiver calculate its own position, it can then determine things like distance, bearing, estimated time en route to a waypoint. A waypoint is a place that you kind of want to go. And nowadays, you know, in your car GPSs, you can just touch your little vehicle. If this is a place you wanted to return to, my favorite fishing, like that, and you can create a waypoint, you can create a name for it, and you can return time and time again to it. Although the GPS receivers use both latitude and longitude coordinates to identify position, so the first GPS receivers weren't near as pretty as these newer ones with all the beautiful colors and moving map displays and whatnot. So the first ones only gave you sort of lat and long coordinates. Now we can name our positions. Like I said, my favorite fishing hole, and a lot more information is available. So the system in itself consists of 3 segments, starting with the space segment, and then somebody's got to control those satellites. We already know who's controlling those satellites. It's the American military. And the user segment. So that's every Tom, Dick, and Harry that's got a GPS receiver. So there's our 3 segments, starting with the space segment, control segment, that's the Americans controlling those, all the satellites, and then the users, and whether those users are on the ground or in the atmosphere, in the air, like aircraft, neither here nor there. Let's look at the space segment. So the space segment consists of 21 operational Navstar satellites and three active spares up there. So there's a total of 24 satellites. So when you think about 24 satellites, so there's 6 different orbital planes with 4 satellites in each plane. 4 times 6 is 24 satellites operating at around 10,900 nautical miles above the Earth's surface. And like I said earlier, they've been set in their geosynchronous orbits so that a minimum of 5 satellites should always be in view to any user anywhere in the world. Yeah, sure, there are some spots that are shielded from this. So there's what we're looking at. Okay, 6 orbital planes, 6 orbital planes? Go back here. 6 planes with 4 satellites in each orbital plane. I'm not about to count all them butterflies, but it looks like there's probably 24 butterflies. 6 orbital planes with 4 satellites in each plane. 21 operational, 3 active spares. I think they're all operational nowadays. So for 2-dimensional navigation, we're going to rely on to pick up with our GPS receiver 3 satellites. Now I'm going to tell you, when we used to install these systems in aircraft, our design engineers said, sometimes you can only pick up 3 satellites. and that only gives you two-dimensional navigation. So we're going to buy, it's almost like a blind encoder, okay? They called it an altitude digitizer, and they install an altitude digitizer into the GPS to provide sort of a fake three-dimensional capability. Was there a question? Okay, so for three-dimensional navigation, you need 4 satellites or more. And again, so what's this picture showing? It said, keep in mind, it's not just aircraft using the Navstar GPS system. It's ships and folks on the ground, vehicles. We want to pick up, you know, if we want three-dimensional navigation, you got to pick up 4 satellites for sure. Okay, we're hoping always for 5 or more. You know, if you only have 3, unfortunately, it's two-dimensional navigation. Like I said, sometimes that happens, even in the air, and that's why we used to purchase an altitude digitizer to feed the GPS system to sort of fake in an altitude and give us our third dimension, our dimension in the atmosphere, in space. Okay, let's keep going. So the space segment, those satellites are continually broadcasting their extreme accurate timing pulses and their location. So the location they are in the geosynchronous orbits. The GPS receivers pick them up and process the data using the delay time between when the signal was transmitted and the time that your GPS receiver receives them. And can then determine, once it's picked up enough of them, your speed, your position on the Earth's surface or in the altitude in the atmosphere, and the altitude of the receiver picking them up, so that the aircraft. So each satellite actually transmits 2 different L-band signals. The signals are referred to L1 and L2. So L-band, if I'm not mistaken, it's a subband of UHF. It's UHF. So L1 is sent at 1,575.42 megahertz, so 1575.42 megahertz. And L2 is sent at 1227.6 megahertz. They call that biphase modulation because it's being sent by on two different frequencies. So each of the 24 satellites that are up there are sending out, you know, biphase modulation with each satellite's own distinctive. You know, I kind of think of each satellite as having its own distinctive DNA. They refer to it PRN, it's pseudo-random noise. So each satellite has a name. They all have a name, and they're sending out their name and their position. So the PRN, the pseudo-random noise, allows GPS receivers to distinguish between each of the satellites and their biphase modulation. 2 types of codes are being transmitted. Okay, CA codes, which are referred to as course acquisition codes. And we kind of get to use those, civilians. And P codes are precision codes, and that's military. Okay. Remember, there's different levels of accuracy, and the military typically retains rights to the higher accuracy. So the P code, which is used by the military, is actually it's operating 10 times faster than the course acquisition codes, the civilian, and can be adjusted for an accuracy of anywhere from 100 meters down to 10 meters of accuracy. So that's the military coding. The course acquisition for civilian use has an accuracy set at around 30. Okay, and again, that seems like a lot. Geez, I'm 30 meters off the mark. Yeah, but I think they're referring to 30 meters in the Earth's atmosphere. Okay, a little bit harder to repeatedly pinpoint your location in the Earth's atmosphere, 3-dimensional. So since there's no control over who uses the GPS system, the U.S. military has sort of designed the ability to manipulate the accuracy of the transmission data. They call that SA, selective availability. you're going to get to use and enjoy what we've selected for you. So selective availability can reduce the accuracy of the civilian codes, the course acquisition codes, anywhere from, meters, and they can skew it out to 100 meters, so they can make it worse. They can change its accuracy at will. And their own precision coding, they can skew it from 10 meters accuracy out to 100 meters as well. Now, to protect against false by foe during times of war, the U.S. military has also incorporated a secret Y code that they call an anti-spoofing code, which could be introduced into the mix if need be. So selective availability, the military's ability to skew, to degrade the accuracy of the GPS in for national security reasons. But as of May 1st, 2000, back in 2000, they might have changed it after the Twin Towers hit. But the U.S. government instructed the military basically to give civilians as good of accuracy as they could. Okay, as they could. So this has increased the accuracy. From approximately 100 meters down to about 20 meters or 65 feet in the air. So around the world, it's not just in the United States, even though they control it. They have 5 monitoring stations, 3 uplink ground station antennas, and a master control station at Falcon Air Force Base in Colorado Springs. That makes up the control segment of the Navstar GPS system. So these monitoring stations are tracking all 24 satellites and calculating precise orbital locations. So where are they? Well, where's the head office? The headquarters is Colorado Springs, not Cape Canaveral, Hawaii. That's another station. The Ascension Islands, Diego Garcia, and I don't know, Kwajalein. I can't even pronounce that. Those are your 5 control segments, your ground station control segments throughout the world. Obviously heavily guarded. And when it comes to the user segments, that's every Tom, Dick, and Harry that's bought a GPS. So aircraft industry for sure, folks on boats, mariners, military, farming, business, auto and truck, transportation industry, including the people that are walking well, or at least small handheld receivers, hiking and whatnot, up into the very complex military systems. So there's a lot of users. And we see a lot of users. There we go. Okay, it's time to go. We can talk about this a little bit more at another point. Okay, so don't forget, for those folks who haven't done the VOR ILS quiz, that's only up until tonight, until 11:59 p.m. And also, there's also the other quiz on the go, which is the Advanced Avionics Systems. And that's up for another week. And later this week, because we've now finished transponder, DME, and TCAS, another quiz will probably come out Friday afternoon. So we're well on our way to success. Any questions? Okay. Off to your next class you go.
See you later, Darren.